Hey guys, Jake here coming at you with another math lesson today. I did a problem very similar to this yesterday, so if you haven't already seen that video, go check it out. I'll put a link up here and in the description so you can check that out. It's going to be the same kind of process, but today I'm going to be showing you how to find local maximum and minimum values of a function. So when you're asked to find the local maximum and minimum values of a function, it's really going to be pretty similar to finding increasing and decreasing intervals of a function, and I have a video on that as well if you want to check that out. But the first step in doing that is finding the critical numbers of the function. So the first thing we want to do is find the critical numbers. Let's say we have this function here, a of x equals x times square root of x plus 3, and we want to find the critical numbers. To do that, we need to find the derivative of our function. So doing that is going to require the product rule in this case. So the product rule says that the derivative of this function, which is the product of these two functions here, right? We have x as one function and the square root of x plus 3 as our other function. The product rule says that this derivative is going to be the derivative of the first piece times the second piece plus the derivative of the second piece times the first piece. So we'll take the derivative of x, which is just 1, times the second piece, and then plus the derivative of this piece. So the derivative of square root of x plus 3, remember, the square root of anything is the same as taking that thing raised up to the 1/2 power. So these two are the same, square root of x plus 3 and x plus 3 to the 1/2. So to find the derivative of x plus 3 to the 1/2, we can use chain rule and power rule. So we can bring the power down in front, lower the power by 1, leave the inside the same, and then multiply this by the derivative of the inside. So doing that will give us 1/2 times x plus 3. We'll lower our power by 1, so 1/2 minus 1 is negative 1/2. And then we'll multiply that by the derivative of the inside. The derivative of x plus 3 is just 1. And then we're going to multiply that by this first piece, so times x. So let's get this out of the way now. So this is the derivative of this function. Let's just kind of simplify that. We'll say a prime is square root of x plus 3 plus, so having this be a negative power means that this is essentially going to be in the denominator. So on our numerator, we're going to have a 1 times x, which is just x. And on our denominator, we're going to have 2 times the square root of x plus 3. Because the negative exponent brings it down to the denominator, and 1/2 power is the same as square root. So 2 times the square root of x plus 3. So this is our derivative. So to find the critical numbers, we need to figure out where our derivative equals 0, and we need to figure out where our derivative does not exist. So there's a couple places that might cause this derivative to not exist. Whenever you're looking at a function like this and you're trying to figure out where it doesn't exist, you want to think about a couple things that frequently cause functions to not exist at certain points. You can't take the square root of a negative number. We have square roots here, so we need to make sure that whatever's inside the square root is 0 or positive. You can't take square root of negative. You also can't divide by 0. So if you ever have a fraction, you need to make sure that that denominator does not equal 0. And lastly, this is another common one. We don't have it here, but it is common. You can't take a log of 0 or a negative number. So if you ever have a log or a natural log, you need to make sure that whatever's in there is positive. We just have fractions and square roots in this case though. So if we're trying to figure out where this does not exist, we have 2 square roots, right? Both of them are the square root of x plus 3. Like I said, we can't take the square root of a negative number, so we need to make sure that what's in that square root, x plus 3, is greater than or equal to 0. Also, we have a fraction. We need to make sure that we're not dividing by 0, so we need to make sure that the denominator of this fraction does not equal 0. So we have these 2 equations that need to hold up in order for this derivative to exist. If either of these equations are broken for any given x value, then our derivative does not exist at that point, and we could consider that a critical number. So first solving this one, we can just subtract 3 from both sides, we'll get x has to be greater than or equal to -3. So any x values less than -3 are not going to work. So we would want to consider x equals -3 as a critical number. That may or may not be a local maximum or minimum. We don't know yet. We'll have to figure that out with the first derivative test. But it should be considered a critical number. So we also need to solve this equation. So we could divide both sides by 2, and that would cancel there. We would have the square root of x plus 3 does not equal 0. 0 divided by 2 is still 0. Square both sides, and then subtract 3 from both sides. So x cannot equal -3. So if x equals -3, we're going to divide by 0, and that's going to cause a problem. But again, that just gives us x equals -3, which we already had as a critical number for over here. So figuring that out just told us x equals -3 is one of our critical numbers. Now what we also need to do is take our function, or our derivative of our function, and set it equal to 0. So we're going to get 0 equals square root of x plus 3 plus x over 2 times the square root of x plus 3. And we need to set it equal to 0 and solve for that. What we can do is, if we subtract the square root of x plus 3 over to the other side, that'll give us negative root x plus 3 equals x over 2 root x plus 3. And now what we can do is multiply both sides by 2 times the square root of x plus 3. And if we do that, we're going to cancel over there. We're going to multiply it by what's over here. If we multiply this times 2 root x plus 3, our square root of x plus 3 times square root of x plus 3 is the same as doing square root of x plus 3 squared, right? Which would just cancel the square root and the squared, and we would just have x plus 3. So what this actually leaves us with is -2 times x plus 3. And then equals x. So now what we can do is just kind of distribute this and expand everything out, and that should give us something a little bit easier to deal with. -2x, if we distribute this -2, we'd get -2 times x. -2 times 3 would be -6, which equals x. Now we can just move all of our x's over to one side, all of our non-x's to the other side, and get x all by itself. So we'll subtract x from both sides. That'll cancel there. We'll add 6 to both sides. That'll cancel with that. So we'll have -3x equals 6. Divide by -3. X equals -2. So x equals -2 is our other critical number. So we have x equals -3 and x equals -2. Those are the only two critical numbers for this function. So now what we need to do is apply the first derivative test to figure out the intervals where f is increasing and the intervals where f is decreasing, or the increasing and decreasing intervals. So to do that, we want to draw our number line. We want to put only our critical numbers on the number line, -3 and -2. Remember, these represent all of our x values. However, the other thing we want to think about when we're now trying to apply the first derivative test to figure out which of these critical values are local minimums and which are local maximums is, let's think back to our original function, which was x times the square root of x plus 3. And remember, we can't take the square root of a negative number. So if we plug in any number that's less than -3, we're going to get a negative number within this square root. If we plug in -3.5, we're going to get negative 1/2 within our square root. Square root of -1/2 does not exist. So actually, anything on our number line over here, we can ignore, because our original function is not even defined for these x values. So any x value less than -3, our function is not increasing or decreasing because it's not even defined there. We can't even get an output of our function at those points. we can't get an output of our derivative at those points either. So there's not really a way for us to figure out if our derivative is positive or negative because it doesn't even exist. So we can actually ignore this whole chunk here. We're only going to pay attention to these two intervals. X's between -3 and -2, and then all x's greater than -2. So what we want to do is plug in these critical numbers into our derivative and figure out if it's positive or negative at those points. So let's just pick any number between -2 and -3. Let's just say we'll plug in x equals -2.5 into our derivative, so into this function right here. Unfortunately, this is not a very nice thing to plug numbers into. I would recommend just using a calculator for this. So if we plug in x equals -2.5 into a prime, we're going to get out a prime of -2.5 equals -0.18, about. It doesn't really matter what the exact value of this is, it just matters if it's positive or negative. So we have a negative, our derivative is negative between -2 and -3. So what that means is our function f is decreasing on that interval. So we know f is decreasing between -2 and -3. And then similarly, let's plug in some number to the right of -2 or greater than -2. Let's just plug in x equals 0 into a prime. So a prime of 0. Doing that is a little bit easier because right here we're going to get 0 plus 3, square root of +3. And then over here, if we plug 0 in for x here, we're going to get 0 divided by 2 root 3. So 0 divided by 2 root 3 is just 0. So this is just the square root of 3, which is a positive number. All that really matters is that it's positive because since the slope, or since the output of a prime is positive, the derivative just represents the slope of the original function. So a prime being positive at 0 tells us that the slope of f is positive at 0, which just means that f is increasing at 0. So our decreasing interval is x equals -3 to x equals -2, and our increasing interval is x equals -2 to positive infinity. So by the first derivative test, since we have this critical number here where f prime is negative, or the slope of f is negative to the left, and the slope of f is positive to the right, this would be a local minimum. So x equals -2 is a local minimum. And this other critical number, -3, is not a local minimum or a local maximum because it's not defined to the left of -3. Even though our function is decreasing to the right, the first derivative test requires that we know what's happening to the left and to the right. So since we don't know, or we do know it's not defined, it's not increasing or decreasing to the left. So therefore, the first derivative test, basically tells us that this is not a local maximum or a local minimum. So in this case, we only have one local extrema, or one local maximum or local minimum, and it is a local minimum at x equals -2. And that's really all there is to the first derivative test to find the local extrema. If you're curious about finding absolute max and min values, I'll put a link to a video where I talk about that.